Now we are going to see on OSI layer, the very important concept of the network. Here the message will be received at each layer, and we will make the decision. So each layer, let the message be M, and the output of the message from the layer will be M dash. We'll see how this is being done and how the message will be converted from M to M dash. So, so when you have some kind of network segment and where only packets can travel at a time, and what will do when the two packets want to travel? This will the scenario you may encounter. So, for example, say two machines want to send messages on this one piece of network segment at the same time. Then somehow we need to arbitrate. Arbitrate means that when you have some kind of network segment where one packet can only travel at a time, and this is what will happen when we want to have the multiple messages which have to be traveled at the same time. So we have to figure out which one message to go first and which is go to the second. So again, there are rules for all these things, and all these rules are embedded inside this network protocol. So the protocol defines the rules, what you do when two machines want to talk at the same wire at the same time. The set of rules is called as network protocol. So when you want to send a machine message from A to B, how do you figure out what the next node is that you want to send your message? Then again, this is defined by the protocols, and it will be having rules which are concatenated. So these protocols are in turn, it's very complicated in nature. And because of this complication, what people have done is they have decided to divide the protocol into layer so that the functionality or the rules can be assigned to the layer. So OSI is called as an open system interconnect model, and it presents what the protocol stack is. So it is classified, divided the functionality into layers. You take all the things that this network protocol do and divides them up into layers. So routing is one of the layer in the OSI model, and flow control is another, and arbitration may be another layer. So it just separate the functionality. So now all of these layers have been taken care of, but the separation is really generally good to do the coding. So because functionality writing one piece of code that handles all these complex tasks in the network, it will be really a messy thing, and to fix an error is again a very tough task. So in order to make simple for the coder as well as for the layman to understand the functionality of the network, it has been divided into different layers. Now the internet has used a similar set of layers, maybe more compressed version, but definitely the idea of all these complicated tasks are divided among the different layer of the protocol, which reduce the complexity so that you can able to manage it is also in a very nice way. So each layer has its own responsibilities, and each layer will use different data. So different data that will be in the header. For instance, if you're looking at routing, there is a layer that does the routing, and you will be need to use this routing information in the header. And actually, this this routing information will be there in the header. Where in the other hand, if you're working on the flow control, and flow controls may be at a different layer, then the flow control doesn't necessarily need to know the routing information, not exactly the all details about it, but it might need to know the capacity of a node. The flow control need to know the capacity of the node, and how many messages can a particular node can take at a time. So that would be a different information that also might be present in the header or something like that. So each are not each message is not in the header, but they definitely each layer uses different type of information for its job. So we take here the message M will be converted into message M dash by passing to the layer. The next thing which you're going to talk about is encapsulation. Might have come across this encapsulation in OOPS concept, but we also have this on the networking part. So we really seen what are the protocol stack kits and really what is it has been defined, why it has been layered. So now we'll go into a little bit of detail in depth. So how the protocol is defined. So then how, why, and why we need to have this kind of protocol layers. So at the least you should know what is a term that is being used around. If you want to make a new embedded system, you say, well, I need a network, internet, which protocol stack I'm going to use. So which implementation of the protocol stack will I use? You should know all of these things when you want to use this IoT and a corresponding protocol. You should know what are the protocol you're going to use and what kind of specific application you're going to work on. So you need to know about what term means and what it get used to a lot when you are actually coding things. You should know basically what it means. So not all details that I'm talking about will be important in the long run, but you should see it all at once because it will give a better context about what you're using. So for example, in the OSI layer concept, the idea about taking this protocol or making a stack, a different layer of protocol, is that you have got these multiple layers, different tasks, and different networking tasks that you have to handle. So these tasks are associated with different layer of protocol, and each layer is implemented usually in software. Actually, some of the lower layers are implemented in the hardware, and somewhere in the hardware or somewhere in the software. So the difference doesn't really matter too much to us, certainly the top layers on the software, but the idea is that the message you want to send is okay. So you make this message, we got our picture which is in the previous slide where the message M is converted into M dash through when it passes to the layer. So this is what the data we want to send. So it is basically an input layer. Let us talk about the first layer. Let's see the first layer, the top layer, so that it gets into it and into the code. So the code get the message, it makes the message a kind of decision of the processing, and whatever decisions are made at the layer, then it puts the results on the decision header of the message, producing a new message M prime. So now the M is much more bigger because it has some extra information. So it has whatever inside M, apart from the content, it is now added some more information by the layer. So it has become M prime and is much more larger. So it has a additional header on that outside, right? The M dash has additional header. So at every level, this happened. Every level, if the message goes, it has been added some information to the header, and its size keep on increasing. So let's see this level in the routing. So how this will be handled in the routing. So the goal of this level is to make sure the message and figure out the sequence of machines that will hop through to get its destination. So at this level, it takes a message, it finds the route. It says, okay, you need to go to the machines A, B, C, and D. All right, that's the sequence. So it can take a sequence, the whole sequence of node, put together into the header of a message, and then put out this message M prime, which is the same old message. See, we have to make the note of this thing carefully. The message will be keep on adding with the header, but if you remove the header alt clause, the message content should not change. It should be the same as the old message. But now with the extra routing message contained inside the header. So that's a general idea that at every layer of a code or the hardware or whatever it is that implementing the protocol will make some decisions like routing information, arbitration information, flow control information. And the results of this will be put into the header or some of the results. It will put directly into the header and we will get to a new message out of which is nothing but the M prime, which is now as a new header. This is done on the sending side. So this is the same idea it will be using at the receiver side where they will be removing this M and one by header as it passes to the layer. At last, you see the M will be reached for the destination. Next, as I said, now we have seen so far now the OSI layer. Now we're going to discuss in detail about the encapsulation. Encapsulation is used to mean that a protocol, they are separated from one another in some sense. As I said, so each layer it has been separated. So each layer, each protocol is separated. So all of these different tasks that need to be performed, say routing, that is mapped to a particular layer. Routing is always mapped to a particular area. As I said, the functionality is divided into layer. This is again performed by the protocol information stack at this layer, and the layers do not have to deal with it. So it is encapsulated, it's separated from the other layers. And the whole point for this slide is to make it simpler to understand or also write code. The functionality is separated, so it is very easy for us to maintain, to write code. So if you are a programmer and you are dealing with this layer that deals with the routing, then all you need to think about is that you need to think about only the routing. You need not think about the flow control, because flow control is the functionality in other layer. So it's really helpful for the programmer when you divide the layers, network functionalities into different layers. So this is what the encapsulation is all about. So if there is some problem in the routing, then the programmer should really look into the routing code, and they need not bother about the flow control. This is how the encapsulation is ensured in the OSI model. Next, we will see how this transmission take place with the help of this encapsulation. So it's again a protocol stack is the implementation of different layers put together. So a transmission, when I want to send a message, basically the message starts at the top layer and then it goes down. So you put the message into the top layer of the protocol, it makes its decision and it puts some information in the header as it passes to the next layer. It chats, makes some decisions and adds header and then continues. Each and every time the message passes to the layer, some information is put onto the header until you get to the bottom of the layer. Now, once the message reaches the bottom layer, that is called the physical layer, and at the layer, it actually takes the data and it put it on the electrical mechanism or a transmission mechanism and through some kind of media so that it reaches the recipient. So that it means one of the two things, either the wire or a physical layer. It codes the data into physical wires, or it encodes into the wireless broadcast, or it radio broadcast, or any other thing which is available to send the message to the recipient. So always at the bottom layer, there is a physical layer which actually transmits the signal either by a wire or by any means of communication. This is how the transmission takes place. Next, we're going to see how the message which is transmitted is being received at the other end. That is what we're going to see in the slide, encapsulation, transmission. Now at the receiving end, the message comes in. Remember, this has been sent by the physical layer of the sender part. So it is on the wires, it's a bunch of electrical signals on the wire, or it is sent through the radio signals. So at the end, the message goes up to the same protocol stack by which is being sent. So by this I mean, when it is received at the physical layer, because its physical signals, either wired or wireless, they come in and then they go upwards. Basically, they have to get basically recoded back to its original data. So now at the receiving end, these messages are going through the protocol stack up from the bottom up. So the opposite of what has done in the transmission part will now take place. And at every layer, the message gets received, the appropriate header information which is being added in the sender part is being read, and that information is being used by the particular layer. And then the new message that's produced is actually smaller than the first message, because as and every time the message passes through the receiver and layer, some portion of the header will be removed. So when the new message is received a layer, it will process on the header and will take some information. So the output will be much more lesser in size. And then it goes up to the next layer, which makes the header information of the layer use it, and then it moves and push it back to the top of the layer. So by the end, at the top all, you will actually have the only payload. All the extra information which is being attached by the center part will be removed, and only you will have the payload. Payload is nothing but the message, because all of the information will be striped off. So that what it will be happening at the receiver end, and it's a reverse process. It is completely the reverse process of what is being done at the transmission side. Next, we are going to see on TCP/IP, which is extensively used in the IoT part. So we're going to discuss in detail about the TCP/IP protocol stack. So we are going to see that through an example. So we want to write a code that accesses the internet. We're going to use this stack, this protocol stack, that is TCP/IP protocol stack. We want to use this internet. So you want to know something, how it works. So it typically, when you are using this internet, this is sort of standard protocol stack that you are going to use right here. This is not same as the OSI layer protocol. This protocol layer has 7 layers and it is more complicated. Then we have a simplified version. We have only 4 layers in it. The top layer is the application layer. Below is the transport layer, where you can see this TCP and UDP. That's the transport layer. Then below that, you can see the internet protocol, which is nothing but the network layer. And then that's the network internet protocol will be placed there. And below that, you can see the data link layer and physical layer. So the very bottom layer that you don't see there is merged into the physical layer, where it is actually drives in onto the wires, and it drives the signals onto the wires or onto the radio, whatever protocol. And actually, if you look at these layers, there's a code associated with each layer. They are typically library functions. So in practice, in this specialization, when you write network code, and you will later, when you work on this network code, we will be talking about, you'll be calling the applications layer library functions only the top layer. You don't have to worry about the lower layers at all, almost all. Just the top layer is what you are really going to be deal with, but the whole stack has been already been implemented and it will be ready for you. So you will download a free stack that looks like this, but the functions you will be calling will be at the top application layer. Next, we are going to see application layer. This protocol supports directly many applications. We want SMTP, we want FTP. All these things will be facilitated by this application layer. But just to say a little bit about this layers, there is an IP we already talked about, that TCP, UDP, and the data links of the physical application layer. These are protocols that directly interact with the applications. So whatever kind of applications if we're writing, if it's a network application, it will have some kind of network protocol, and if it's an application layer protocol, that it's worked with. For instance, name some application protocols such as SMTP, Simple Mail Transfer Protocol. This is a protocol used by many of the clients. If you have got an email client, it might be using this SMTP to communicate with the email server. HTTP, Hypertext Transfer Protocol, and you will see this in the URL and your address bar on the web. So anything that uses HTTP will do the web interaction, which is most likely used in the class. That's we will discuss in later of the discussion. We'll discuss. Then we have LPD. It's another one. It's nothing but a line printer daemon. The printer talks to each other using the protocol. The printer can even communicate with the help of the personally designed line printer daemon protocol. But there are a lot of this protocol, file transfer protocol, a bunch of them. If you want to transfer files, maybe you will use the file transfer protocol. Hopefully, yes, FTP, that's nothing but a secure file transfer protocol, because it is better than the FTP, which transfer the file in a much secure way. But the idea is that every network application has its own protocol at the application layer that it uses. That is what the ultimate summation of this slide. Next, we have application layer example. The below given is the figure which will talk about how the payload or message is being added when it added with the header when it passes to different layer at the sender side. So to give an example, what one of the protocol look like, let us have a little bit on have a discussion on HTTP. This is HTTP. If you look at the request on the web, little hard to see, but then if you look at, actually the one of the things we are looking at here is nothing but the response message. So the figure it as a response message. It has several lines. Actually, the code right there has 6 lines. The top 3 lines, the one in the green, and those are the headers. The bottom line in the white, those are the body, data, the payload. So whatever term you want to use, the header are going to be basically the top 3 lines. Now the header information, it gives information about the message, but it is not the actual content. So for instance, we look at the first line. It gives you the protocol version, and it also gives about the message type. It says 200 OK is it is talking about the HTTP protocol. When you Google, you can get a very large protocol document, whereas in that it will say 200 OK as a particular meaning. Each and every code has a particular meaning in the header. Every response message is going to have a particular code, and similarly 200 OK is sort of your code response. So the next line you can see date, and then date were transmitted. And the next line you can have a content length, shows that how big the data is. That's inaccurate, but then that's an example. This example is an example. It may not be accurate. It all have the content length, and there are a lot of different pieces of header information you can stick into the header. Then if you look at the body, it will contain the data that you are going to send, and that contributes to the actual body of the message and the context or the context of the message. Now, with this example, which is very common, if this is a web, you're asking for a web page, what happens in your machine, your IoT device, let's say, send a request out of the web server, and the server sends back the content of the web page. When you have submit a request, the response will have to be thrown out. And so when your IoT device can render the page and draws it for your screen, and so that what you see there is the HTML code, which is the content of a web page. So this is summarized, but you can see it starts with HTML, hence with HTML. And it has a bunch of HTML tags. If you're familiar with those things, but that could describe a web page. So if you had a web browser on an IoT device, it could read the data and then draws a web page represented that it's supposed to represent it for you. So this is all about the application layer protocol and the header and the message. Next, we have the mobile hardware network in detail. As I said, it is for self-configuration. It has been used extensively. So think mobile hardware network and how they are used in the Internet of Things to connect the Internet of Things object, the bigger network, to the Internet will be discussed. We'll also talk a little bit about how the code that we're going to write be in the classes, and how it won't directly know the details of these things, because you will be writing generally high level code, but still it is important for you to be familiar with the concept. So the mobile hardware network, or a MANET, is a self-configuration network. And I say self-configuration, means the size and the routing table will get updated now and then based on the components which is connected, because it is very dynamic and it has to do update its routing table as and when the nodes are being added. By self-configuring, we mean that the host in the node in the network configure themselves, because they are moving all around the time. So their connections, their connectivity may change across the time. So far, in the picture, you can see a bunch of nodes. You can see cell phones, you can see car, flight, whatever IoT devices, there are a set of them. And then at the top middle is the access point. So this access point is the thing that connects our MANET to the main internet. Now a MANET could be just independent and now connected to the network at all. But most commonly, we are going to be connecting to the internet some way through an access point. Now the access point is typically not a mobile. It might be much larger than it, or it may be a wireless connection, so that all the IoT devices can be connected, but it might be the wired connection also. So the access point maybe isn't mobile, but everything else. And the way I have shown the diagram here, I have lines between the two nodes. If they are connected, they can communicate directly with one another, meaning if they are in the radio range and they have communication can take place. So it should be within the range so that you can be connected. So sometimes, for instance, you look at the cell phone all the way on the left versus the right cell phone on the right. You don't have edge directly between them, because maybe they are out of the range, because they are both within the range, and they can able to communicate each other. The connection between these components changes all this time, because these things are moving. And the two cell phones couldn't talk to each other, because we have a cell phone and it can be reachable only if it is connected to the network. If it is not connected to the network, we will not able to connect, and will say then it is out of the network coverage. That is what all the point I'm trying to say here is. The next slide will be talking on the major issues with the MANET, or the issues, general issues that will face the MANET. So, the main aspects of MANET is the power. So you really have to worry about the power you're talking about the MANET, because in MANET, each of the device are highly unstable. Similarly, this IoT device, they are all mobile. They are all running off batteries, and the batteries can run out because whenever you do configuration, it needs some amount of power consumption. So that easily your device may run out of the power. So you have to generally change the protocol to be more power restrictive. So selecting the protocol for the IoT is very, very crucial. It has to save your power somehow. So the changes a lot of way you do networking. So you send less data, for instance, you are restricted to send less data because every piece of data you send, that is going to be some kind of power consumption from the device. So the battery is the very heaviest part that will be, you will be very worried about when using the MANET. Next, you also discuss about the data rate and the security. The data rate talks in detail about how the wireless bandwidth is used and how this wireless bandwidth consumes power of the device. That is what we're going to see. Extension, and we're also going to talk about the security. So in addition, you typically have lower data rate because you're going to use less power. You have to send data more slowly. So you have a less of data, lower data rate. As an example, sort of a Paul bar in Bluetooth. So you are familiar with the Bluetooth, I think, right? I hope you are all familiar with the Bluetooth protocol, so that you can really appreciate the Paul bar in Bluetooth. So Bluetooth, it uses again, it's a protocol which functions on low energy. It's a network protocol again, and it's wireless. Bluetooth low energy is another. It's also a network protocol derived from the Bluetooth, but it's very low energy version of the Bluetooth. So the Bluetooth, you can send a video across the Bluetooth. You can get enough data rate sent to transmit it, even the video as well. Now Bluetooth low energy, there is no way that you can send at the same rate, data rate. It uses lot less power, but you get a low data rate. So you can send the video. So the fact you are going to low power restrict you in terms of your data rate, and that restrict your functionality in a lot many ways. Security is often a major concern in the internet. So you want to do encryption, then it will, again, for encryption need a lot of power consumption, whereas this IoT devices are not that much efficiently equipped with the power. So security is a very big question mark in this MANET. Networking program in practice. So actually in the application level, we write code, and this code will majorly use the library function which is available. For example, we have many different library functions, and two are discussed here: send message and receive message. When a send message will create a TCP IP and transmit, and the receive message will receive the TCP message and it will return the content. We have seen extensively on TCP IP, and we need seen why we need networking. Now we're going to see IoT protocols. Before we proceed into the IoT protocols, we need to have some few definitions so that we can easily understand the concepts. First is nothing but endpoint. Endpoint is nothing but a device. We can say here it is a sensor device. Endpoint is a thing. It is a connected thermostat or any sensor which creates or generates the data. Next is access point. Access point is the radio that is receiving the data from the one or more sensors, and it is usually connected to the internet. The access point are those which receives the data from the sensor, and you need to be connected to the internet. And next is nothing but the third is backend. So once the wireless data are getting to the access point, it has to send to the server through an internet. For example, onto the cloud platform. So where a program is running to do these kind of things, the data has to be transmitted from this access point to the backend server with the cloud storage platform. So that is called cloud storage, is generally called as the backend. So there are many extensive protocols available in IoT, and we have listed only few, and it is not enough any particular order. So, for example, Bluetooth, BLE, ZigBee, Z-Wave, 6b.mp4, Thread, Wi-Fi HA, 2G, 3G, 4G, LED CAT 01 and 3, LTE-M1, NB-IoT, 5G, NFC, RFID, SIGFOG, wireless, and another enormous number of protocols. And we are going to see some of them in brief here. Bluetooth and BLE. Bluetooth is global 2.4 gigahertz, and it's a personal area network. Maybe it will only serve for a certain signal range. It cannot be done with a high range. It is only with functionable with a limited range. And it's a wireless based communication, and it's you can able to transfer file based on this Bluetooth from device to device, and wireless headsets also basically functions on this Bluetooth, and as well as a wireless speaker are all able to function with the help of the Bluetooth. Next is nothing but BLE. It's a another version of the Bluetooth, and it's basically designed for the low power devices. And, since I said it is basically designed for low power devices, only less number of data can be transmitted with this protocol. And this has been mainly designed to conserve power, and it mostly remains in sleep mode whenever the device is not getting activated. The third is nothing but the ZigBee. It's a 2.4 gigahertz protocol, mainly works on the mesh network. Mesh network is nothing but the connection between the nodes in the network are very clumsy or tightly coupled. We can say it's a mesh network. It was originally designed for building automation and for controlling things. And it is like thermostats, wireless thermostats and lighting system mostly use the ZigBee. Next, we have Z-Wave. Z-Wave is a sub gigahertz mesh network protocol, and it is a proprietary stack. It is mainly used for home automation, and wherever we need to build an application which security is the main concern, then Z-Wave is mainly preferred. Next is 6LoW PAN. It's a lightweight IP-based protocol, and used for to travel over the lower data networks. It is an open IT network protocol like ZigBee, and it is primarily used for home and building automations. Next is Thread. Thread is an open standard built on IPv6 and 6LoW PAN protocol. It if you think of it as a Google version of ZigBee, you can also think you can actually use some of the chips for Thread and ZigBee because they are based both on 802.15.4 protocol. Next is Wi-Fi HA protocol is designed specifically again for the low rate data rate, and it is for it is also accommodate long range sensors and controllers. 802.11 HA is far more IoT centric than many other Wi-Fi counterparts. Next, we have 2G GSM. 2G, though it is very old, this TDMI introduction is making it much more popular, and ATMs and old alarm system use this. And in most parts of the world, it is phased out and are in process of being phasing out, but still it is being used in the IoT. Next, 3G and 4G. I know 3G was the first high-speed cellular network, and it is a name that the technologies refer in IMT 2000 standards. 4G is a generation of cell phone standard that's followed by 3G, and it's vast, and this is the most used network nowadays. And you know the 4G's speed is really appreciable. Next protocol is nothing but LTE CAT 01 and 3. With LTE classes, the lower the speed, the lower amount of power they use. Then like LTE CAT 0 and 1 are typically suitable mostly for IoT devices. LTE M1, it's the first cellular wireless protocol that was built from the ground, especially for IoT devices. It's really built for IoT devices. And they say that this protocol is not available yet, and so hence the performance cannot be commented. And it is worth understanding since because it is built from the scratch for the IoT devices. It worth understanding the carriers and the hardwares and the base stations, all are taken into consideration. So here upgrades can be done entirely through the software, and this really helped with the infrastructure cost because companies won't necessarily need cellular base stations, just a few endpoints are enough. Next is NB-IoT, or we can call it as narrowband IoT, is another way to tackle this cellular machine-to-machine communication for low-power devices. It is based on direct spread spectrum sequence, a modulation similar to the old newer version of weightless W. So Huawei, Ericsson, and Qualcomm are the active components of this protocol, and they are putting a lot of efforts to really bring it up. Next is NFC and wireless HAT. It's NFC is nothing but near field communication. It's a IoT network protocol used for very close communication. If the devices are very close, then this NFC can be used. Next, wireless HAT is built on a hot communication protocol, and it is what the company considers the industry first international open standard wireless protocol. Next is RFID. There are two types of radio frequency identification. One is active and passive. Other is a passive. This protocol was designed specifically so a device without batteries could send signals. I said, right, this RFID, one of my lecture in the first slide, I said this RFID is used in logistics. So whenever you use RFID, you need not have antennas, but then if you attach it, the antennas, which is embedded in RFID chip, will itself be able to send the signal in a particular range. In most systems, on one side of the RFID, the system is powered, creating a magnetic field, which induces an electrical current in the chip. This creates a system with enough power to send data wirelessly over and over again. And next is nothing but Sigfox. It's a global IoT operator, and it uses differential binary phase shifting keying in one direction and Gaussian frequency shift keying in another direction. The Sigfox and their partners set up antennas and towers and receives data transmissions from devices such as clocking sensors and water meters. The next IoT protocol is nothing but LoRaWAN and Ingenu. LoRaWAN is a media access control protocol designed for large-scale public network with single operator. And Ingenu was created something called random phase multiple access, which uses direct sequence spread spectrum, and it is similar to the code divisions of CDMA. Before IoT was a thing, Ingenu was selling metering infrastructure that collected low power information from electric meters. Next protocol on IoT is that weightless N, P, and W. So weightless N is an ultra narrowband system that is very similar to the Sigfox. Instead of being a complete end-to-end enclosed system, it is made up of a network of partners. Next, WLSP is the latest wireless technology. It offers two-way features and then quality of service tiers. And next is weightless W. It's an open standard designed to operate in TV white space spectrum. Next IoT protocol is ANT and ANT plus and Navy. So if you have a Samsung device, you probably have a radio, right, with their protocol in it. ANT and ANT plus seem somewhat like other type of BLE system designed to create networks that piggyback off their existing hardware. There are a lot of devices have ANT and ANT plus compatible chip in them. And the idea is that if you get enough space of these radios added to the world, you can use them as a mesh. Next is the MV IoT protocol. It's a microchip proprietary network protocol. It was created for short-range networks and designed to help customers reduce the product's time to market. Next is N-Ocean and Dash7. N-Ocean is a protocol designed specifically for energy harvesting applications that are extremely low power. Dash7 is an open source wireless network protocol with huge RFID contract and is mainly used with US defense. So among the protocol, we have taken some of them and we have compared with the frequency, data rate, data range, power usage, and the cost. And this will give a quick idea about this protocol. And if you ask me which protocol, IoT protocol is the best, I have really no pinpoint answer for this, because the internet protocol has been keep on expanding for the globe and for the past 5 years. So there are more than dozens of IoT protocol which is coming, which has been there, and every year there are few protocols being added to it. So if we ask which protocol is best, and I would say that these protocols as we choose and based on the application. We cannot choose a single IoT protocol for all kinds of application. Based on the applications, you have to choose the protocol. That will be a very apt point of choosing with respect to the applications. So in my point, I think IoT experts have started to call for a global protocol standardization. Since there are many protocols being developed for IoT, and these IoT experts put together has submitted a global standardization. But I don't think that this global standardization is going to work out with IoT, because it differs with the application, and this standardization is it's all it's the need of the hour, but then I don't think with this developments in IoT, and it's very specific to the platform, I don't think it will materialize. Just as there are newer and newer application and use cases coping up with this IoT industry, fit for IoT protocol for the deployment, it's a long way. Again, it is emphasized that the safe and effective device management is the keystone for sustainable IoT development worldwide. Therefore, the business knowledge it's a very crucial thing to choose the IoT protocol, and we cannot pick the best from it. It all depends on the application. A quick summary of today's session: networking and internet in IoT. We have seen how the communication is taking place between the IoT device till the cloud server, and we discussed extensively on various networks, LAN, WAN, MANET, and the client-server architecture. We also discussed about the IoT internet protocol stack. We discussed in brief about the list of available IoT protocols and a quick comparison among the protocols, IoT protocols, and we are also seeing how we can choose this IoT protocol. So with this, these are my references been used in the presentation. And thank you so much for the passion listening. And if you want to reach me, you can reach me at tiago@cutn.ac.in. Thank you so much for the person listening. We'll meet on day 5 webinar, which is all about the research avenues in IoT. Thank you.